So we're going to look at solving exponential and log equations. And so just a small hint, if the graphing calculator has given you most of the answers on your contagion project, this should help enlighten you on how to do some other things. So first we're going to look at how to solve these equations. Notice that both of these equations are exponential. And these would both fall into the category some might call nice equations. And the reason I would say that they're nice is because even though the sides don't match, we can rewrite them with the same base, and we've done this before in class. So like 1 over 25 can be 5 to the negative second power. And the reason I would choose that is because I see on the other side there's a 5 to the n minus 5 power. Then I would simplify any exponents that need to be simplified. And then once I have the same base, if these powers are supposed to be equal, then the exponent values would need to be equal, so I'll set them equal to each other, and I will finish solving for n. Negative 5n equals negative 5, so n is equal to 1. And in part B, you can see something similar. Now 32 is not a power of 16, but both 16 and 32 are powers of 2. So I could rewrite 16 as 2 to the 4th power. And I could rewrite 32 as 2 to the negative 5th power. Then, again, we'll simplify any exponents where needed. So like multiplying together the exponents we see here. And now that we have the same base and the power should be equal, we can set the exponents equal to each other. And then we can finish solving for n. Now, sorry, that should be a negative 4. So n is equal to negative 9 over 8. However, we all know that it's not always going to work out that these numbers are the same. If I make a slight change in those numbers, like I changed the 16 to a 17, all of a sudden that problem is unsolvable by using this method. So if you look at both these problems here, they're unsolvable by that method. However, our properties of our logarithms can help us out. So basically, since logs and exponents are inverses, what we want to do is when we're having trouble solving an exponential equation in exponential form, we want to rewrite it in logarithm form. And if we're having a problem looking at it in log form, we want to rewrite it in exponential form. So like in part C, it's in exponential form. I have no idea how to solve it because I can't rewrite the bases. So what I'm going to do is rewrite it in log form. You can either actually rewrite it in log form, or you can take the logarithm of both sides, and in the end, you'll be getting the same answer. Now you might think like, oh, this doesn't help. Made it more complicated. But remember, we have a property with logarithms that if there's an exponent or a power here, we can rewrite this as 3x times the log of 5 equals the log of 823. So the log was actually helpful because it kind of released the x from being in the exponent, and then I could solve the equation without x in that exponent position. Now to isolate x, it's being multiplied by two things, a 3 and a log of 5. So I'm going to divide by both of those factors. Now this log is a log base 10, don't forget. Okay, your log's got to have a base and the number you're taking the log of. So the 3 will cancel, log of 5 will cancel, so I will have that x is equal to, and if you weren't able to use a calculator, like on the standardized test you're used to taking from the past or something like that, you would leave your answer like this. If you are able to use a calculator, you would go ahead, you would punch this into the calculator, and you would get a result. The result would be 1.3903. It can get a little more complicated, like you see in part D. So here, first of all, I'm going to remind you that a square root means an exponent of 1/2. So this is like 5 to the x minus 3 power all to the 1/2 power. Okay. So some people at this point, I've seen a couple methods. I think what I've decided I like is I like to just square both sides and get rid of that 1/2 exponent. So that gives us 3 to the power of 2x equals 5 to the power of x minus 3. So 3 and 5 cannot be written with similar bases. So again, we're going to take the logarithm of both sides. And again, that seems silly, but in the end it's very helpful because it allows these exponents to be rewritten as factors multiplying those log quantities. Now in this problem, this is a little more difficult because x shows up in two places. So just like you would in any other problem, what you want to do is you want to get all the x's on the same side of the equation and maybe the numerical values on the other side so that you can solve it. And that's going to require distributing the log of 5 so that you have one part of it that's strictly numerical, 3 log 5, and the other part that has the term with x. Now both these terms with x you're going to want to get on the same side, so I'm going to subtract x log of 5 from both sides so that I can have all the terms with x on the same side. So I have over here a 2x times log of 3 minus an x times log of 5. Now, that doesn't mean it's easy still because look at what I've got. I mean, I can't combine the log of 3 and 5. They're not like terms. They're very different. So what I can do here to get x by itself is I can factor the x out of those terms so that then I'm going to have x times some really big complicated number that has logs in it and all of this. But remember, it's really just a number because you could put it into the calculator. Okay. So we have a 2 log 3 minus a log of 5. Now remember, the stuff in that parentheses, that 2 log of 3 minus log of 5 is just a really complicated number we could get from the calculator. So you have x times a number equals what's on the other side of the equation. So we're going to divide by this really long, complicated number on both sides of the equation. So this cancels out, and we have x equals. And again, if you weren't using a calculator, you would keep this expression as it is. Otherwise, you would put it into the calculator, which I am doing now. Being really careful to use parentheses in my denominator so that all of that stuff you see written in the denominator actually gets used in the denominator. And I get negative 8.2144. All right, I'm going to leave the word problem to see if you guys can figure it out. And that's going to be what we discuss in class on Monday, in addition to doing some homework and working on maybe your contagion project. All right, so now let's talk about solving log equations. So just like exponential equations, if you have the same log with the same base on both sides of the equation, you can just set the quantities within the logarithm equal to each other. So like in this first equation, if those two things are equal, 2x plus 1 must equal 3x minus 5. And then we can finish solving this. And we would get that x is equal to 6. Now with your log equations, you have to be a little more careful in your checking. And the reason is logs have some more limitation than exponents. Remember that we cannot calculate the log of a negative number or the log of 0. So again, as I've said many times, a good math student will check their work because checking is just part of being complete. But here you actually really need to check your work because if you're not checking, you might get one of those extraneous solutions. You didn't do anything mathematically wrong, but it doesn't really fit the scenario. So what I'm going to do is plug 6 in for x for each of these and look at what I have. So in the first, on the left side of the equation, 2 times 6 is 12 plus 1 is 13. And on the right side, 3 times 6 is 18 minus 5 is 13. So you can see that not only do they look the same, which makes me feel good, but these are both things that could be calculated. I don't know what log base 7 of 13 is, but I could figure it out using a calculator or something like that. So 6 is a good solution, and I'm going to keep that. So I'm going to work out part B the same way. If those two logarithms are equal, then x squared minus 14 must equal 5x. This is a quadratic. So I'm going to set it up so that all things are on one side of the equation. This quadratic happens to factor, so that's pretty nice. And so I'll get solutions of 7 and negative 2. Now, I'm not going to stop here and immediately eliminate the 2 because the 2 itself is negative. what I'm going to do is check that when I plug it back into the equation, does it create a situation that's undefined or has no solution? Does it give me a log that I cannot calculate? So let's say I'm checking first x equals 7. Again, I'm going to plug it into both sides and see what those logarithms look like. So if I plug 7 into the left side, 7 squared is 49, and 49 minus 14 is 35. If I plug 7 into the right side, 5 times 7 is 35. So this works. Okay, I get the same thing on both sides, and they're both calculatable. If I plug in negative 2 to the original equation, let's look at what we get with that. So if I plug in negative 2 to the left side, negative 2 squared is 4, and 4 minus 14 is negative 10. And on the right side, 5 times negative 2 is negative 10. Now you might feel like this worked because both sides look the same, but ask yourself, what is log base 8 of negative 10? There is no power you can place on 8 to make it equal a negative. Remember, we couldn't calculate logs of negatives or of 0. So it's not that the 2 was negative that made this an extraneous solution. It's more that when I plugged it into the equation, it created something that's not calculatable. Therefore, the 2 is extraneous. And I'm just going to keep the 7 as my solution. Now, not all logarithmic equations are set up this way. They might not have 2 logarithms in them that you can set equal to each other. Instead, they might look like part C and D. So if we look at part C, this is one log equation. So I can't just set 5x plus 2 equal to 2 because there's not a log on the right side. So again, when we struggled with exponential equations and we couldn't solve them just using exponents, we resorted to logarithms. Same idea with logarithms. If we cannot solve the logarithm equation just using logarithms, then we're going to resort to exponents. So remind yourself that log base 2 of 8 equals 3, okay, which is the same thing as saying 2 to the third power equals 8. You can rewrite a logarithm in exponential form. So when I look at the problem up here, remember that log with no base is really the common log, or log of base 10. And so this would be 10 to the second power equals 5x plus 2. Now this is solvable. I know that 10 to the second power is 100. I will subtract 2 from both sides. So I'll get 98 equals 5x. And I'll divide both sides by 5. And I'll get x is equal to 98 over 5. Okay. Now remember, I want to check this. All I really want to know is that when I plug it in, it doesn't give me an extraneous solution. So if I check this, 5 times 98 over 5 plus 2 equals 2. So this is log, the 5's will cancel out, so I have 98 plus 2, which is 100. So is the log of 100 equal to 2? Yes. So this is a good solution. All right, now part D is confusing because there's numbers, there's multiple logs, lots of things going on. But don't forget that your properties allow you to take these 2 separate logarithms with base 10. Remember, I don't have to write that base if I don't want to. And we still know that it's base 10. And combine them together. Now, because they're being added as separate logarithms, when I combine them into one logarithm, they are going to multiply. Z times z plus 3. Okay? So this will be the log of z squared plus 3z equals 1. And now this problem is a lot like part C, that I don't know the answer. I'm struggling with the log part of it, so I want to switch it to exponent. So I have a base of 10, a power of 1 equal to z squared plus 3z. So this is 10 equals z squared plus 3z. I have a quadratic, so I'm going to use it solving my quadratic methods. I'm going to try factoring, e to the square, quadratic formula, whatever works for me. So in this case, it is factorable, giving us solutions of -5 and +2. Again, I would want to check that if I plug those in, they work. Now, if I plug in +2, I'm going to show you like my short version of checking here. When I plug in +2, I have the log of 2 plus the log of 2 plus 3, which is 5, equals 1. Now, I don't know if the log of 2 plus the log of 5 equals 1. I actually could go ahead and figure out that that's true. But I at least know there's no extraneous solutions here, so if I did my algebra correct, I know I'm good. Whereas when I plug in negative 5, my problem says the log of negative 5 plus the log of negative 2 equals 1. These both are not calculatable, so this solution is extraneous. So I'm just going to keep that z is equal to 2. Now notice I did not plug them into the combined equation. I plugged them back into the original equation because that's what I was asked to solve. And I need to acknowledge that those negative values won't work in that equation. Okay? All right, so when you guys come back on Monday, we're going to be working on homework number 6. I did post an assignment sheet in the announcements part of our Canvas page. So if you want to get a head start on that, you can look at that. Otherwise, we will be working on that on Monday, and we will look at your final review.